Swayam Prabha. Digital India. Educated India.
So we have the, we will mirror later the structure, okay? So I will just make the left part and we will mirror everything. So we have the members defined, also tapering. Let's do supports. There are two types of supports that we will use. There are those supports that you would typically define in every software. In this case, these are the supports at the column base. That's obvious that we need their supports. The supports can be found in the structural members top page, and there is this nice icon which looks like a pinned support. Then you click on it, and on this screen there is a combo box where by default fixed is written. If you click on the combo box, then a list is populated which contains a set of predefined, most commonly used configurations for the different degrees of freedom. What we will need is, of course, we want to support the displacement of the column base in each three directions, and also around rotation around the vertical axis. Now at this moment it's already important that Consteel can always and only work in 3D. So there's no such option that even if I design a 2D frame, I can limit the model to 2D. And many softwares have this option, but in Consteel we don't have, because you will see why. So we select the X, Y, Z, Z, Z. That means restrained displacement in each three directions, which these are considered as global directions because this symbol is selected. As I said also yesterday, we could have user-defined and local, but we stay with the global, which is the default. X, Y, Z, and Z, Z means that rotation around the global vertical Z direction. So X, Y, Z, Z, Z will be fine for us. That means that we don't make any fixation against rotation, and also warping is free. It can appear. Now it's a good question if it's true or not, but that's probably the easiest assumption. And then once we selected this already predefined configuration, I just click on the line of the column. If this much nicer visualization is selected, it has a disadvantage that sometimes you don't see the lines and the colors. So personally, I always, once I somehow made sure that my structure is as I want, I always switch off these, or at least I go back to this representation to not have a solid symbols and see the lines behind. And now it's much easier to select the point. I click on the point, and there is a symbol made here. If you zoom in, then you can see a bit better. But you can make each of these symbols be smaller and bigger by playing with this slider here at the bottom. If you zoom to the biggest, then you can see that it is really displacement with these arrows in the three directions, plus there is also a rotation and restraint around the vertical axis. Okay? Now this is the support what you would normally do in every software, but in Consteel we will need to do also other supports, because Consteel is a 3D software. And we will perform linear buckling calculation, even if we define only in-plane loads, which will create only deflection in the plane. As we saw in Consteel, if you want to perform buckling calculation, which is hopefully you want, then the only way in Consteel to get there is to perform linear buckling calculation, but linear buckling calculation is really 3D problems. Even if this is just a 2D structure, the displacement will go in the weakest direction of the structure, which is always out of plane. So we need to also assign out of plane supports. Now, what are the out of plane supports for these structures? Typically, there can be a lot of things, but typically wall and roof purlins, so the point where these are adjusted. Of course, here we assume that those purlins cannot move along their length because they are somehow connected to some bracing, to some roof diaphragm or something. But as a consequence, each purlin line can be considered as a lateral point load. And then, in addition, we will also consider that those purlins which have flange braces, A flange base is typically an angle or any sort of profile which is connected to the inside flange of the eye section, and in a diagonal direction close to 45 degrees, it connects the bottom flange of the eye section to the roof purlin. Its main role is that if the bottom flange is in compression, it wants to buckle laterally. This buckling will not be allowed if I connect this part of the rafter which wants to move laterally. I connect it by an additional element to the purlin, because then this lateral displacement will only happen, or can only happen, if at the same time the purlin is bent. So the bending stiffness of the purlin will limit or will completely eliminate the rotation capability of the section. Now, if we somehow assume at this moment that you will follow and you can satisfy the stiffness requirement of the AISC, and then you will define a rotational and a point stiffness, point support rigid enough, then here for the calculation we can assume and model them as completely rigid lateral supports, okay? So at the moment we will assume that those are like that. So therefore, for all those positions where the purlin or the girth is attached to the rafter, we will assume a lateral out-of-plane point support to the external flange. And in addition, at every position where we have a flange brace, we will add another lateral support to the inside flange, okay? So at some positions, we will have support on the external flange only, and at some locations, we will have two supports, one to the external and one to the internal, okay? This is very important. If you don't make these supports, then probably even the first buckling calculation will fail, because the whole structure can fall down, or even if it runs its critical load multiplier will be 0.0000000, neglect, so nothing wrong. Okay, that's not what we need for the slenderness. So let's define out-of-plane supports. Again, these are supports, exactly the same supports as the one we already defined. So we come to structure member point support. But instead of the X, Y, Z, 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 we select the Y. The Y is the global Y axis, which is at the moment out of plane direction. And but we don't want to place the support on the reference. If I click anywhere on the member, then you see immediately graphically that the support was positioned on the reference line. So this is my reference line with a lot of effort. This is the internal, the inner line with quite a lot of CAD functionalities I finally managed to do. This is the reference line of the members. If I don't define any additional eccentricity, then every object which is attached to the member will be positioned to this line. Now that's not what I want. It's even better visibility support if I change to the solid representation and I look from behind, and then it's really visible that the support is not attached to the upper flange. That's not what I want, so now I delete it, because I will need to define also an eccentricity, not just the position, but also an eccentricity. So I go back to the support, and in order to define eccentricity, I can click on this drop box, and it has several options, but it's probably more graphically understandable that instead of clicking here, click on the three dots, and then you have such a visual symbol where you can just simply select the top flange here. So it will be here, but not exactly here, because the support itself, we will not assume that it happens immediately at the bottom flange, because actually at the bottom flange there is the purlin, which has a certain height, and it's probably more fair to assume that the supporting effect will be provided at the center of gravity, at the level of the center of gravity of the purlin. So that means that's an additional 100 millimeter eccentricity. So therefore, we say the top of middle plus an additional 100 millimeter. Okay. Now this is fine. Now let's be fully perfect. I delete it, because the distance of the first purlin was defined along the slope, which is funny, and because that 200 millimeter on the top is not 200 millimeter at the third line level. So now, because we started earlier from what I made in the PDF, we have now the external line, so we can do it precisely. So let's make first a line at the, wait, how the hell can I do that? Okay. Again, I I draw a random line somewhere to be perpendicular. Maybe you don't need to follow it. I will tell you finally what will be the value to use. Okay. Now I move this line from here to there. Now I move the line from here along the line L and 200. Now it's here. And now this way we found the intersection point. That intersection point in reality is at 90.1 millimeter from my line. So actually you don't need to do this exercise. You can do immediately the definition of the first purlin. So we will, even if on the drawing it seems that it's 200 millimeter, at our level that's only 90 millimeter, okay? So we will position the first purlin at 90 millimeter, and for the rest is already fine because the two lines are parallel. So we go back to structural member, out of plane support, select the Y, top middle 100, and now I would need to click at 90 millimeter from the end. Now, it's not so easy to click at 90 millimeter from the end just by eye, but there are some helper functions. As I said, this N is not always N. It can be changed into many things else, including also into a D. If you click it twice, then the N becomes D, and that means that this is a distance function. I can change the 1000 into 90, press and enter, and that means that Consteel will place points along the line at 90 millimeter, okay, from the end, but that's not good because at the moment my line of the end is here. So first of all, I need to make sure that my line will really start from the intersection. Okay, at the moment you see the line itself is longer, so even if I have this beautiful 90 from the end function, this will start to measure the 90s from here. But I don't want to measure it from here, I want to measure it from the intersection. Okay, so first of all I will trim the lines to start really from here. We can also trim it, but there is also another nicer function that we can move points and edges with this function. So we select this move point and edge, click on the end of the line, and go back to the intersection when the intersection is switched on. And then I made the line shorter, and I can at the same time do also with the other line. I click on the end of the line and come back to the intersection. Now the lines will not be longer anymore. They will really have the end where I want. And now with this beautiful 90 function, I will be able to place the support really at 90. Okay, so why? So have you managed to make this edge point and edge moving? So this command, move point and edge, select any of the ends and move them to the intersection. And then repeat the same with the other line. Okay? I'm stupid because I wouldn't have done it because it's actually the length of the line is exactly 200. So don't do that. There's no need to make any trick. Just enter 200 and don't trim it and just click on the so easier. Okay. So forget everything what we did now. Okay, so structural member, point support, Y, top middle 100, not 90 but 200 into the D, approach the line from its end, and Consteel will show the red dot. Go to the red dot and click on it. Okay, now we will have a support which is visibly made of an orange line which is going into the sky, and then this very well-known symbol for the restraining in the Y direction is placed on the top of it. Why? Because when I switch on the supports representation, then we will see that this is really placed at its real location. So the support is really positioned at the level where it is physically located. As you can also see that this is it really in the middle of this gap. That's the gap of the 200 millimeter which we kept to incorporate the space for the purlins. So now we have the first one, and now the rest is relatively easy, because for the first 1, 2, 3, 4, 5, 6, 7 times, we can make a copies of 105 millimeter along the slope. So I select I go back to a much easier to understand representation. I select my support. I go to the copy, but instead of 1, I will change the 1 to 7, because I want to, I don't know if it's maybe only 6, doesn't matter. So to 7, start the base point, and now I need to say that it must be 1,500. What do? I start to go on the line, press L, and enter 1,500. And as a result of that, I will have plenty of supports positioned. If I don't want to see these many dots at 200 millimeter anymore, I change the N, click on the D to turn to N, and I keep maybe the N equal 2. That means that only the middle lines are shown. So now I here have many supports, and then I have one more additional at 1 meter. So I select the very last one, again come to copy. The 7 is lost, so it's automatically anyway 1, so it's fine. I click on the line of the intersection, I start to move along the line, press L, and enter 1,000. And now we have one more support there. Okay? Now this was the purlin provided lateral point support. Now let's do also with the flange braces. As it is visible on the picture, we have a flange brace on the 2nd, on the 5th, and then on the 7th, 8th, and the 9th purlin. That goes very easily. That's, and again, a support. As we said, this will be another lateral support, but this time attached to the bottom flange. So point support Y is fine. Instead of top middle, we will select the bottom position. We cancel the 100 millimeter because this we don't need. We assume that you can make it nicer. You can deduct the flange thickness a bit more. You can do what you want, but I will not be so precise. I just change it to 0, and the only thing I need to do is that I click on the position of the 2nd, I don't remember what was on the 5th, and also on the 7th, 8th, and 9th. As you can see, Consteel knows that this is a taper member, so it will know automatically the height of the tapering, and therefore it will place the supports accordingly. And that's not just that it knows what is the actual size, but it knows also that when I changed it, and I changed it to maybe 1,200, and it will be deeper. No, it didn't. That's a bug, unfortunately. But normally, it should have moved also the support. This, unfortunately, it's not a fully maintained version of Consteel, and this was already. So this is not so intentionally it should follow, because it's a. We didn't say that the distance is a certain millimeter from the reference. We said that it is at the actual bottom level. Now, if I change the profile, assign another profile, make a tapering deeper, then this instruction is always reevaluated, and everything is moved to the actual position as it should be. So I don't need to make the change. Unfortunately, it seems that this doesn't work in this version, but that's by intention it should work. Okay, and now let's see the column. On the column we have, that's the column what we checked today at the beginning. It has 2 supports, one at 2.2 meter of height and another 1.5 meter above. So let's again go support. Let's define first the supports on the external flange. So the Y, top flange, again another 100 millimeter of eccentricity, and let's say that at 200 millimeter high. What do I easily do? I change to distance 2,200, enter. I search for my point, and I click on it. So this is now 2,200, because 2,200 is the instruction to put the point. And I start, it's always important to So if a line is maybe 3,000 millimeter long and I say 2,000, obviously if I start from this end, then 2,000 will be here, and there will be another 1,000 from here. If I start from this direction, then there will be 2,000 and 1,000. Consteel will always place the position starting the line from the end, which is closer to my actual position of my mouse cursor. Okay, so that's why I always approach my mouse that line of the object from which I want the measurement to be made. Okay, so that's why I always came close to the line from below, and then the point appears. If I do it from the reverse direction, then you see that the red point appears here at the higher position. The red point is now here. The point disappears automatically after 3-4 seconds. But it's very important, and that's very easy to make that mistake. So it's not just enough to say the distance, but you need to also show this way from which direction you want to measure the distance. So it's 1,500, and the other is at 3,700. So I just simply change the 2,000 to 3. Again, I start from the bottom. I look for the red light to appear. I quickly go there, and I click on it. And now if I want a flange brace, it's easy. I just change to go to the inside. I eliminate the 100, and I click on both positions. Okay? Now if you see the solid view, then we can see that we have many, many symbols. If I'm not happy that these are so big, I can make them smaller or bigger. And now these are the lateral supports. And now if I want to mirror everything to the other side, actually I do exactly the same like what I did at the beginning with these. Now one support is still missing. I still need to put here a support to the corner. That will be a bit tricky, but not complicated. Just again, it comes another specialty of Consteel. I come again to point support. Again, I select Y. Again, I select top. Again, I select the 100 millimeter. And normally, I click to the intersection. But when I click to intersection, no support is placed, but another question is asked. It says select the structure member. Obviously, at this location, there is not just one member, but there are two. Consteel has no idea which one I want to refer my connection, especially that I said that it must be at the top middle of one of the member, but Consteel doesn't know which member I want, so that's why it's asking another question. I need to click this time on the column. Once I click on the column, then it is placed here. If I was clicking on the rafter, then this point would be moved here. Okay? Exactly here in the corner we cannot put. So in the reality, probably the support is there, but there is no structural element there. Now we are we are at the moment to mirror everything. I can also just simply select everything. That's the simplest. Doesn't matter if there will be some extra lines. Doesn't matter. So I select everything. Come to the mirror function. And we will be ready exactly at 6 o'clock. I click on the line, press X, 0, enter, and we are ready for today. To save your model, File, Save, or Save As. If you save, there are two options depending on what sort of license you have. Probably most of you have at the moment a student license, and for student license typically you can save to the cloud only. Okay, those who purchase commercial licenses, they can save it also to computers, of course. The reason why we have this cloud is that we have another software called SteelSpace. This is for an online sharing of projects and collaboration and such, and the idea was that it's also an introduction to this functionality. Plus, those who are sharing their models to the cloud, then and if they share this project, this model with the teacher, then they don't need to send maybe homeworks as email attachment, which is a bit boring, but they can just upload the models to the cloud, and And if you work with a teacher who is controlling or checking or approving your calculations, then you can easily share with them and not as emails. Okay, so you can do only to the. I will do also to the cloud because that's the only thing you can do. So select cloud, save, and then Consteel is connecting into the still space function. Sometimes it fails for the first, then you can start it again. Unfortunately, it has some issues sometimes with the different network settings, firewalls and such. So as you see also now it appears as empty. If it doesn't work, then again just simply close and try again. For the second time usually it works, you see. It's what a trick. And then now you can have also folders. You can do everything what you want. There are also some default models already provided by us, which are visible here. Some of them are in Hungarian, so that's a bit of confusion. But you can always create a model for you, yourself, or you can just save it here. You can say frame. You can put also some text, a description, something, and click on save. And then this will be saved on to this cloud folder, okay? So this was for today. And tomorrow we will start with loads, and then we will start to do also calculations. What's the main purpose? Okay?